again. And the last presentation of this session is given by Michael Sprlak on solving a geodetic problem, downward continuation with a Grail and LoLa data. Please.
All right, so let's go to the moon now, also known as Fegari in Greek. So good afternoon, ladies and gentlemen. My name is Michal Sprlak and I work at the University of West Bohemia in Pilsen. Together with Shinchan Han, Pavel Novák and Martin Pitoniak, we used Grail and LoLa satellite data to resolve the convergence-divergence problem for the analytical downward continuation of the external spherical harmonic expansions. Let me start with a brief introduction. You certainly know that the external spherical harmonic expansions are probably the most popular mathematical parameterization of the gravitational potential and its spatial derivatives. The convergence domain of the series is the space above the minimum Brillouin sphere. Nevertheless, we commonly employ these expansions even inside the bounding surface. Justification of the analytical downward continuation procedure has been debated for decades. Overall, conclusions among theoreticians and pragmatists in the literature are completely contradictory. In this work, we revisit this topic by employing the most recent topographic and gravitational observations of the moon. The analyzed quantity is the line-of-sight acceleration. It is the difference of two gravitational gradients at two different points projected onto the unit vector B connecting these 2 points. The delta operator indicates the spatial difference of any quantity below. We compared 3 kinds of these accelerations. The first set comes from the Grail satellite mission, which was the lunar equivalent of GRACE, mapping the gravitational field of the moon in 2012. We formed the Grail accelerations from the intersatellite ranges ρ, position vectors x, and their time derivatives, all available from level 1b and science orbit data. I note that these measured accelerations are completely independent of any mathematical parameterization. In addition, such experimental data were used for the very first time to test correctness of a mathematical apparatus. The second set are accelerations generated by the lunar crust and calculated by the Newton integral in the box. The crustal masses are bounded by the LoLa topography from the top and by the spherical crust base of radius 1680 kilometers from the bottom. Radii of these two surfaces are the variables of the isotropic kernels HT and HU under the surface integral. BR, B phi, and B lambda are the components of the unit vector B, and alpha is the direct azimuth between the computational point and an integration element. The crustal masses have uniform density of 2550 kg per meter cubed. I note here that such forward modeled accelerations are exact everywhere in 3D space, meaning that they are completely free of any divergence issues. The third set are accelerations synthesized by the spherical harmonic expansion in the box. The spherical harmonic coefficient C and M are inferred by crustal masses identical to those for the Newton integral. We calculated the harmonic coefficients by our rigorous forward modeling approach up to degree 1800. To avoid any numerical instabilities, we implemented the X-number algorithm for calculating the spherical harmonic functions y and m. I recall that the convergence of the external spherical harmonic expansion is rigorously guaranteed only above the minimum Brillouin sphere. We analyzed the three kinds of accelerations at two 24-hour segments of the Grail satellite mission. The first time series on December 1 is specified by a relatively high orbit. The satellites flew from 4 up to 14 kilometers above the minimum Brillouin sphere. The right figure illustrates the signal power of the three accelerations. We can see that the signal powers of the three accelerations are close to each other up to around 0.16 Hertz. Beyond that frequency, the curve for Grail linearly increases due to the high frequency measurement noise. On the other hand, the signal powers for the accelerations by the two mathematical parametrizations, that is for the harmonic expansion and for the Newton integral, agree very well in the whole frequency range and gradually decay. I'd like to add here that the highest frequency on the horizontal axis corresponds to the spherical harmonic degree 1650. Let's take a look at the coherence spectra between the Grail accelerations and those by the two mathematical formulas. They both show identical behavior and approach unity between 0.02 and 0.13 Hertz. The coherence is reduced below 0.02 Hertz because the processes in the lunar core and lunar mantle dominate here. The coherence is also reduced above 0.13 Hertz, obviously due to the measurement noise. The right figure illustrates the three accelerations again, but they are now high-pass filtered. This is a truncated segment around the 12th minimum of the orbital height. We can clearly see that the accelerations by the two mathematical parametrizations agree very well. In contrast, the Grail accelerations have much higher amplitudes because the measurement noise overwhelms the gravitational signal at this relatively high altitude. The same pattern actually repeats over the entire time series on December 1. So far, we have not seen anything surprising. The second time series is from December 14, when Ebb and Flow were orbiting at an extremely low altitude. The spacecraft literally oscillated around the minimum Brillouin sphere from around -7 up to +9 kilometers. The right figure shows the signal power of the three accelerations. These are practically identical up to 0.2 Hertz. Above this frequency, only the accelerations by the Grail measurements and by the Newton integral agree very well and gradually decrease. Surprisingly here, the signal power for the accelerations by the harmonic expansion increases at the highest frequencies. Let's take a look at the coherence spectra again. The accelerations by the Newton integral highly correlate with Grail. The coherence is higher than 0.8 up to about 0.23 Hertz. Then the coherence decreases as the measurement noise leaks in. On the other hand, the coherence between the Grail accelerations and those by the harmonic expansion is reduced already starting from around 0.17 Hertz, as almost half computational points are located below the minimum Brillouin sphere. We interpret this degradation of the coherence as a failure of the harmonic expansion. In fact, the increasing signal power on the previous slide indicates a possible divergence of the harmonic expansion at the highest frequencies. To support this claim, the right figure illustrates the free high-pass filtered accelerations. This is a truncated segment around the third minimum of the orbital height, meaning that all computational points are located inside the minimum Brillouin sphere. We can observe that the accelerations by Grail measurements and by the Newton integral now agree very well, while the accelerations from the external spherical harmonic expansion provide grossly erroneous values. We also inspected the high-pass filtered accelerations at the other orbital minima and found the very same behavior that actually proves our claim. So finally, we came to the conclusions. In this talk, we examined the justification of the analytical downward continuation, and we did so by analyzing three types of line-of-sight gravitational accelerations, namely those from Grail measurements, the Newton integral, and the external spherical harmonic expansion. We clearly demonstrated the failure of the external spherical harmonic expansion inside the minimum Brillouin sphere. We proved that Grail measurements are sensitive enough to detect this issue. By our knowledge, Grail is the very first gravitational sensor to resolve this long-lasting theoretical conundrum. Overall, we have to be very careful when using external spherical harmonic expansions inside the minimum Brillouin sphere, at least on the Moon. In this presentation, I focused on the analysis along the Grail orbit. However, we have already investigated the analytical downward continuation problem for the external spherical harmonic expansions from different perspectives. To those who are interested in our further numerical experiments, I may only recommend to look into our article which got published in Earth Science Reviews last year. That is all from my side, and I'd like to thank you for your attention.
Okay, thanks. So, theoretical topic, questions? CK?
Yeah, very nice paper, I read it. Thank you for a nice talk. So my question is that your external potential combines the topography and the gravity data, correct? It is sort of in a forward modeling, not an immersion. Is that correct, generating to up to degree 1800?
So the line of sight gravitational accelerations
No.
from Grail,
Right.
all right, I said we compare three kinds of accelerations, okay? So the Grail accelerations, that's pure measurements,
Yeah.
okay? Then those from the Newton integral, that's forward modeling, all right?
Okay.
And those from the external spherical harmonic expansion is from forward modeling as well.
Right, that's what I was talking about.
Yes.
So forward modeling. So if someone comes up with I think JPL has a 1100 with actually inverted, not forward model. I wonder whether that would make some difference in your test. Maybe not. So I'm just curious.
That's actually this. I have also looked into another analysis. I have done another analysis which considers global models in terms of degree variances, all right?
Right.
And that part includes probably what you want to hear.
Right. So I understand Moon is a better terrestrial body for this kind of work than Earth. So that was why I asked the question.
Sorry, repeat the last.
The Moon is more isostatic than the Earth, so you can use topography to
Yes.
approximate
Sure.
gravity field much better.
Exactly.
So that's why I asked this question.
We actually based this study on the assumption that the correlation between the observed gravity and the gravity modeled from topography is almost perfect, right? Which is valid for the Moon.
Yeah. Thank you.
Very good. More questions? If not, we are already in the break time. Thank you again. And we reconvene at 4:30.